So we talked about average and instantaneous velocities. It only makes sense. We go one more step and talk about average and instantaneous accelerations. We started out with the fact that if we had some position function, let's call it x, let's call it r, it's a vector, that could have some x component in the I direction plus some y component in the j plus some z component in the k direction. What we saw is that we could find the velocity as a function of time simply by taking the time derivative of this. And what we get would be dx dt plus dy dt in the j plus dz dt in the k. And we can rewrite that as the velocity in the x direction plus the velocity in the y direction plus the velocity in the z direction, k. Alright, so we need to know how to do that. If we're given any function as a function of time, so it's position as a function of time, then we can take the derivative with respect to time and get a vector function for the velocity. And we can plug in any time t and actually get a vector answer for the velocity at that instant. Well, let's take one more time derivative. If I did so, we get the acceleration as a function of time. So that would be either the second derivative of x with respect to time, if it was two derivatives, right? The second derivative of y with respect to time, and the second derivative of z with respect to time. We can rewrite that as the first derivative of velocity with respect to time. And we need to put an x subscript on there. Don't lose your subscripts. Once you go from position function to velocity to acceleration, make sure you don't lose your subscripts. So that would be the first time derivative of velocity in the x direction plus the first derivative of velocity in the y direction with respect to time plus the second time plus the time derivative of the velocity in the z direction. And then if we wanted, we could write it like we did this one right here. Acceleration is a function of time would be the x component plus the y component plus the z component. Okay, that is our vector definition. So if we're given a vector that has functions of time or components, either or, components that are functions of time, then we can take derivatives, and I'll show you we can actually integrate too. So we can take derivatives to go this direction, and we can integrate to go this direction. Now you know how to get from a position as a function of time to velocity as a function of time to acceleration as a function of time for a vector. Okay, let's take a look at another definition that we're going to see a lot, and that is our average accel. And we can say that's equal to a sub average. Okay, well, we can still do this in vector form. This would be equal to the change in velocity over the change in time. And what is that? V2 or V final minus its initial velocity. Those are vectors. And all over delta t. So we can just rewrite this as the average acceleration is equal to delta v over delta t. So if you know something's at some time t what its v is, and at some time at a different t what its v is, or velocity, then we would use an average acceleration. If we had something given to us as a function of time, we would take time derivatives. Okay, I'm going to do an example in the next problem. I'll be right back.